Physics 101 Collisions homework set number 12 is talking about something kind of new. We're talking about an equilibrium where something is balanced. So we've had equilibrium situations where something was just sitting on a desk and the normal force up equals the gravitational force down, or maybe the frictional force equals whatever the applied force is. When you're at an equilibrium, the net force is zero. But there's also something else. When something is rotating or wants to rotate, then we have not just forces acting on it, but something called a torque. And torque uses the Greek letter tau. Tau looks like that to represent what that is. That's this right here, that tau. So torque is going to equal the force vector cross the length of the lever that's being rotated. In other words, it's going to equal F times L times the sine of the angle between the two. In this case, we have, it's sort of like a seesaw or teeter-totter. We have a pivot point here in the middle, and we have weights hanging on either side, kind of like a balance or a scale. And we're asked to calculate the torque, the total torque, or the torque caused by a variety of different forces. One of the cool things is, just like we can pick our origins and our coordinate systems and our positives and our negatives, we can pick wherever we want to be the axis of rotation. Generally speaking, we pick the actual axis of rotation because that makes the most sense to do. But this problem has us calculating it based on a variety of different axes. So it says calculate the torque from this mass hanging here, and then this mass hanging there, and from the weight of the meter stick, and from the pivot point pushing up. So, I'm trying to erase stuff. We know that if it's balanced, if it's not moving, then the total net force equals zero. F net equals zero, which means if we add up all the down forces, it'll equal the up forces. Well, we can actually figure out the down forces because we're given in this problem the mass, and we're given this mass. So we know the force from gravity of this is going to equal m times g, and the force of gravity from this is going to equal m times g. They're different masses, but we're going to figure out what the force is. Your numbers will be different than my numbers, but we can calculate a value for that force. We're also given the mass of the meter stick, and the meter stick's center of mass is right there in the center. So it's going to have a downward force acting right there at the center, and we can calculate what that is too, because we're given its mass, the mass of the meter stick, times g. So we're going to get values for each of those numbers. The force of the pivot holding it up is going to equal Fg for number 1 plus Fg for number 2, the thing we calculated here, plus the thing we calculated here, plus Fg for the meter stick, which we calculated there in the middle. So all of the downward forces are going to add up to that upward force. That's step one. We need to know the forces. So calculate those forces for your problem. That's step one. Step two, we're going to find the torque. It has us find the torque with an axis of rotation chosen here, at the actual axis of rotation right here, and then at the very end, way down there. Fun fact, it's not going to matter. They're always going to end up being zero. If it's in equilibrium, if it's balanced, it's going to be zero. But we got to check that. So, like, spoiler alert, I gave you that last answer. But let's double check. It also says that we're choosing the counterclockwise direction to be positive, which means that any forces or torques that make it want to turn to the opposite direction of a clock. So in this case, it would be like spinning in the direction of that arrow is plus. All right, so starting with the 0 point on the ruler, on the far left of the ruler, we want to calculate the various torques from the various forces. There's 4 forces, so there's going to be 4 torques. Notice that all of them are perpendicular to the ruler, to the meter stick. So if they're perpendicular, the sine of 90 is 1, and that term drops out. So all we need to do is multiply the amount of force, which we just calculated as the weight, times the distance from our chosen pivot point. So for the first one, this is the distance right there. It's at the 20 centimeter mark, so the distance is 0.2 meters. So F0, 1. That means F with the pivot point at 0 of force number 1 is going to equal the gravitational force that you just calculated, Fg1, times the distance from the pivot, which for mine it's at 20 centimeters, so it's going to be 0.2 meters. And you're going to get an answer in Newton meters, blank Newton meters. It's a pretty straightforward multiplication, but if that's the pivot point on the end and that force is pushing it down, if that was the only force acting on it, then it would cause it to rotate clockwise. So that's going to be a negative torque. So, oh no, that's not a force, that's a torque. I gave it the wrong label. All right, so that torque equals the force of gravity times the distance from the pivot, and it's going to be negative because it's making it rotate negatively. Tau 0, 2 would be due to the second mass hanging down. You calculated the force, so you know how much force it is. The distance, it's at 70 centimeters for mine. It says it right there. So the distance is going to be 0.7 meters. You multiply those two values, but notice if that was the only force acting, it would cause the meter stick to rotate clockwise, so it's going to be a negative torque. You can do the same thing for the force of gravity of the meter stick. It's going to be acting at 50 centimeters. And the pivot point, notice that one is pointing up. And if that was the only force acting on it, it would rotate counterclockwise. So that one's going to be the only positive torque in those first four. The next part of this problem has us picking the pivot point right in the middle at 50 centimeters, the actual pivot point for this balance, so that's convenient. You calculate the same way. The distance from the pivot for the first one, for number 1, is that distance. So if it's at 20 and the pivot point's at 50, that's a 0.3 meters or 30 centimeters. They're 30 centimeters apart. That yellow is hard to see. I'm going to switch back to, I'll switch to blue. So 0.3 meters is going to be the distance from the pivot. This one for me is at 70, that's at 50, so it's going to be 0.2 meters for F2, or tau 50, 2. The ones that would make it turn counterclockwise, the positive direction, there's only one. That would be that one right there. Force 2 would cause it to go in the negative direction. The pivot and the meter stick are both acting at the pivot point, so the distance from the pivot is 0. And that tells me right away that the torque is going to be 0. The last 4 ask you to calculate if the pivot point was on the far end, and I think actually, given what I've told you, you can do that one on your own. I hope that helps. Send me any questions you might have.